Hi everyone, in this video we're going to be talking about how to interpret inverse functions using graphs. So let's start out with a really simple example. Here's a graph of a function. This is the graph of y equals f of x. The first thing I want to do is to fill in the function table for this graph. So when x is -1, we want to know what f of x is, so what is y? And if we look, it's -1.5. When x is 0, y is -1. When x is 1, y is about 0.5. When x is 2, y is 1. When x is 3, y is 2. And when x is 5, y is 3. I skipped 4 just because there's not a distinct point. So now if we want to come up with the function table for the inverse function, what we're asking for is, so my input is going to be the output of the previous function. So if I'm inputting -1.5, what I'm asking is, what x value gave me -1.5 as an output for the f function? And that was -1. So we could say that -1.5 comma -1 is on the graph of the inverse, just like -1 comma -1.5 was on the graph of the function itself. So notice we're just switching x and y like we did when we were coming up with inverses algebraically. We switched the role of x and y. So if x is -1, then I'm inputting -1 into my inverse function. So I'm asking, what is f inverse of -1? Or in other words, what is the x value that gives me -1 as an output for f? So that's 0. To get 0.5, x was 1. So when I plug 0.5 in, f inverse of 0.5 is 1. F inverse of 1 is 2. F inverse of 2 is 3. And f inverse of 3 is 5. So the function table is just switched from the function table of f of x. I flipped the x and y columns. Now what's neat about this is this function table now allows us to graph the inverse function because each pair gives us coordinates on the graph. So let's go ahead and plot each of these points for the inverse function and see what we can observe. So the first point I'm going to plot is -1.5 comma -1. So that's going to be about here and there. Then I'll plot -1 comma 0, 0.5 comma 1, 1 comma 2, 2 comma 3, and 3 comma 5. And I know that each of these were connected up in straight line segments. So I'll connect them up. And do you notice anything interesting about these graphs? Is there some kind of symmetry? There is. It looks like there's symmetry about this line, this dotted line that I just drew in. And if you look, this dotted line goes through the point 1, 1, 2, 2, 3, 3, 4, 4. So this dotted line is y equals x. It turns out that this relationship of the functions f and the graphs of the functions f and f inverse, that they're reflections of each other over y equals x, this is always true. So let's record that as a rule. The graph of f inverse of x is a reflection of the graph of f over the line y equals x. And why is this true? Well, it's a little bit complicated, but I'll try to explain This isn't so important to understand as long as you understand the relationship between the function tables for the two and how that makes the graph of f inverse a reflection. But here's why it's true. If a comma b is on the graph of a, or on the graph of f, sorry, what that means is that b equals f of a. That's just what it means to be on the graph, that this point satisfies that b equals f of a. When I plug a in to f, I get out b. Then we can say that a equals f inverse of b. That's the definition of inverse. So f inverse of b is just the x value that I plug into f to get out b. So this tells us that this is true. But what does that mean? So then b comma f inverse of b is equal to b comma a, because this is a, but this point, if b is my x value and then f inverse b is the y value on the graph associated to this x value. So then b comma a is on the graph of f inverse. So this is a little bit of a complicated explanation, but I trust that if you want to understand it completely, if you just stare at this for a little bit and play around with some more examples, it will start to make more sense to you. You'll understand why this explanation is the reason that this relationship holds. And that this relationship holds, that if AB is on the graph of the function, then BA is on the graph of the inverse. Okay, so let's do some examples of how we might use this rule. So my goal here is to draw the graph of the inverse function if each of these is the function f. So in the first example, I have this sort of curvy function. It's not really a parent function or anything that we recognize, but I know that I can get the graph of the inverse by drawing in the line y equals x and just drawing the reflection across that line. So the inverse will look something like that. Now similarly, this is one of our parent functions. Well, it's close to it at least. 1 over x looks like this. So this is the function f equals negative 1 over x. Now if I go to draw the inverse, what do I find? Well, if I try to reflect this piece over y equals x, I get this piece. And when I reflect this piece over y equals x, I get this piece. So we find that f inverse equals f. Their graphs are the same. So this is a particularly interesting example. We could even check this algebraically. So if I do f of f inverse of x, and I'm saying that f inverse is the same as f, then I'm doing f of negative 1 over x, which is negative 1 over negative 1 over x, which is negative negative x, which is x. So this function is its own inverse. We can see that both graphically and algebraically. Let's do another one. So here's a line, and I get the inverse graph in exactly the same way as before. I'm going to draw in the dotted line y equals x as a reference, and the inverse should be the reflection of this over that line. So it's going to look something like this. F inverse. So something to notice about this example is if you have a line with slope less than 1, then the slope of the inverse will be greater than 1. It's steeper. One last example. So this looks like one of our parent functions. Maybe it's f of x equals x squared, an example we've seen a lot of. when we've been talking about inverses. Now, if I try to draw the inverse graph of this function, or the graph of the inverse of this function, I'm reflecting over the line y equals x. So the reflection of this piece is easy to draw. It's going to be something like that. And then this piece, when it reflects, will be something like that. So this is f inverse of x. What's the problem with f inverse of x, though? It's not a function. This is exactly the issue we came across before. F inverse of x sent 2, well, 2 is probably over here, sent 2 to both 4 and negative 4. So we see why the horizontal line test works. For the function f of x, if we draw a horizontal line, it crosses the function in 2 places. That was supposed to indicate to us that there was no inverse function unless we were to restrict domain. If we look at this horizontal line, if it goes along with the function as we do the inverse, as we get the graph of the inverse by reflecting, the horizontal becomes a vertical line, which tells us that the inverse graph does not represent a function. So that's an explanation for why the horizontal line test works. Another thing to notice about this is if we did restrict the domain, so let's say we were looking at x squared only for positive x values. Oops, this marker's not quite working. So let's say we look only for the positive x values. Then when we reflect it, we get just this piece, which is a function, and we know what that function is. This is the square root function, square root of x. So it does work still to get the inverse function once we have restricted the domain, so the function passes the horizontal line test. So I hope this helps. Please let me know if you have any questions, and we'll keep on moving through those problems.